Electricity. It's a major part of life, from the things we consciously do and interact with, to every function of the brain, such as our thoughts and actions. Brain cells send off electrical signals to control everything that happens in our bodies, and everything that we do. Electrical charges from the brain determine every action and decision that we make, which makes it very important to find out how these signals form. It all starts with two forces, diffusion and electrostatics. Diffusion relies on a principle known as the concentration gradient, which is that ions will flow from a place of high concentration to a place of low concentration. Electrostatics is the idea that like-charged ions repel and oppositely charged ions attract. These two principles are almost always at war with each other when it comes to ion movement. But what does ion movement have to do with the brain and electricity? To answer that question, we need to zoom in. A little more. There we go. This is a cell membrane. For the most part, both sides are electroneutral. Every positive charge is balanced out with a negative one, and vice versa. However, small imbalances collect near the membrane on both sides, which causes an electrical charge to build up across the membrane. This voltage is called the membrane potential, and it is the charge that will eventually be sent as a signal. It's measured in millivolts, using the outside of the cell as the ground. So if the inside of a membrane was 40 millivolts less positive than the outside, the membrane potential would be negative 40 millivolts. That's not it though. Remember diffusion? All those potassium ions outside want to rush inside so that they can flow with a concentration gradient. And they totally could, except electrostatic tendencies force some of these ions back outside. This is because as the inside of the membrane gets more and more positively charged, electrostatic forces keep more from going inside. Whoa. This is chaos, but there has to be a way to fix it. Enter the hero of today's story, the Nernst equation. This equation tells us the exact membrane potential at which diffusion and electrostatics are equal. This potential is called the Nernst potential. So let's reset everything. We'll say that Z, the valence of potassium, is 1, and that the absolute temperature is 310 Kelvin. Furthermore, we'll put 10 millimoles of potassium inside the membrane and 100 millimoles outside of the membrane. Plugging in these numbers into the equation, we can see that the Nernst potential for potassium in this scenario is 61.51 millivolts. That membrane potential gets sent off as an electrical charge to perform a certain task, like having you breathe or talk. Now, in the time that you've been watching this video, you've performed this function over 540 trillion times. So the next time that you're doing anything, like breathing or being alive, take a moment to wrap your head around the hundreds of billions of cells doing this function over and over again every single day. Oh wait, your head is already wrapped around your brain.